So the today's topic is Introduction to Crash Simulation using ls-Dyna. Basically, it includes the structural crash modeling in ANSA, solver in Dyna, and post-processing in MetaPost. Basically, CA part consists of pre-processing, solver, and post-processing. This is a very big topic, so we cannot cover in 45 minutes. But at the end of the day, we will learn about a brief introduction to CAE crash analysis. These are all the webinar contents today. The introduction to crash simulation, where you can see about different types of crash tests, and followed by the key principles of ls-Dyna. So where we talk, I'm going to see the structure of Dyna, say like keywords and how it starts, how it ends, and the unit systems and other stuffs. Now is preparing a structural model. Yeah, this is our CAE part. So we need to prepare a structural model for crash analysis by having the meshing, connections, contact definitions, boundary conditions, and output requests. So once you build your model, you should submit your job. Before that, you should go for a model checking in order to eliminate the basic errors. So OEM has a different setup for running ls-Dyna jobs. So supercomputing will do the solver part. So no need to discuss in much detail about in running ls-Dyna jobs. But once you get the results, we need to do the post-processing the results. So what's the important aspects to post-process the results, and what are the important parameters to check? So let's quickly go through these points here. And finally, how to get into this domain. So I will give you some basic introduction to this part finally. The next item is, as I said earlier, introduction to crash simulation. So here we are going to see some important crash test. So what are the important crash tests? Frontal crash, side crash, rear crash, roof crash, and pedestrian protection. So other than that, we have so many crash tests, but I picked some important one so that you will have some basic introduction about this crash test. What is frontal crash test? A frontal crash is the most common crash resulting in a fatality. As you can see here, there are I picked some 3 important crash tests, but other than that, we have so many frontal crash tests. Why we did this frontal crash test? So vehicles usually impact a solid concrete wall at a specific speed, but this can also be a vehicle impacting vehicle test. This full frontal rigid barrier. So based on the accidental data, they create these types of tests. So this represents the vehicle to vehicle, full collision test. And the next one is ODB. It's nothing but offset deformable barrier. These tests in which only part of the front of the car impacts with the barrier, let's say vehicle. These tests are very, very important as impact forces remains the same as with the frontal impact test, but a smaller fraction of the car is required to absorb all the. The next one is SORB. What is SORB test? This is small overlap rigid barrier. This is where only a small portion of the car structure strikes an object, such as say like pole or a tree, or if a car collides to the other car in a 20% overlap. But it loads the most force onto the structure of the car at any given speed. I would say out of these 3 tests, SORB is the worst severity load cases, because only a small portion of the car is having the energy absorption parts. So mostly the load is getting directly close to the occupants. So occupant will get more injury in SORB allocation. So we should be very careful in these load cases, always in CAE domain. And the next one is side crash. So as you can see here, I picked these 2, side rigid pole and side deformable barrier here. I think there is one. So this is this picture is taken from a side rigid pole, where you have a pole with 20 miles per hour speed at 75-degree angle into a 10-inch diameter rigid pole. Usually the test vehicles slides sideways into the car. So in the real-time scenario, when the brake applies, the car slides and it goes and hit the tree. So this replicates this test. But actually in side crash, it's more severe than the frontal crash. The tough job is like protecting people in side crashes is always challenging because the sides of the vehicles have relatively little space to absorb energy and shield occupants, unlike the fronts and rears, because in front and rear we have a substantial crumpled zone. So as you can see here in the front locations, we are having a number of parts before the occupants, same like rear. So we have some rear crumpled zone in order to reach the rear occupants. The main ratings criteria for side crash is the engineers look at three factors to determine the side ratings. Basically, the driver and passenger injury measures, head protection, and structural performance. We should be always careful in side crash. It's more severe than the frontal and rear. Yeah, this is one of the example. Side deformable barrier. Say like this is a real world picture. Side vehicle is hitting to the car. But if you don't have a side curtain and a side airbag, occupant most likely go for fatality. And the next one is rear crash test. It's one of the most common crash modes. Rear seat occupant will get more injuries and minor threat to fatality. This is mainly for fuel system integrity, let's say. It's intended to check the fuel spills, fuel tank deformation, and any stoppage contact in and around the fuel tank in order to avoid the post-crash fire. So if, as you can see, if your car, if fuel is spilled over to the ground and due to the enormous heat, so there is so much of probability to catch a fire. This crash test is mainly for fuel integrity test. For rear deformable barrier, nearly 1,400 kilogram barrier hitting the vehicle with 80 kilometer per hour speed at 70% overlap to the vehicle. Same like for full rigid barrier, they're applying 1,100 kilogram weight at 56 kilometer per hour with 100% overlap to the vehicle. As you can see in the picture, this is a typical rear crash picture. Mostly here the occupant will not get much injuries, but they're mainly doing it for fuel tank integrity. The next one is roof crash test. This replicates the rollover scenario. Thousands of people are killed each year in roof must be able to maintain the occupant's survival space when it hits the ground during rollover. In the test, what they will check, the strength of the roof is determined by pushing an angled metal plate down on one side of the roof at a slow and constant speed and measuring the force required to crush the roof. So they apply force on the ram on the roof, and the good rating requires the strength to weight ratio of at least 4. Basically what we will do, the roof must withstand a force of at least 4 times the vehicle weight before the plate crushes the roof by 5 inches. So if it's less than 5 inches, then it's fine for this test. So occupant will not get much injury. Crash test is pedestrian protection. As I said earlier, pedestrians are particularly risk in traffic always. In such a crash, a standing or walking pedestrian is struck and accelerated to the speed of the car and then continues forward as the car brakes to halt. Here, the pedestrian is impacted twice, first by the car and then by the ground. But most of the fatal injuries occur due to interaction with the car. That's why they go for a lower leg barrier, upper leg barrier, child headphone barrier, and adult headphone barrier. So the vehicle bumper first contacts the lower leg of pedestrian. They choose lower leg barrier. The leading edge of the hood hits the upper leg. They choose upper leg barrier. Adulthood and childhood are struck by the top surface of the hood or windshield. So this is very, very important. So every OEMs must possess this test and pass this test. Otherwise, they cannot sell their vehicle in their country. So they are always giving a preference to pedestrian. Here comes to our part, correlation to test with CAE. Why do we need CAE? Correlate to test. So CAE, so in order to avoid the prototype cost, And because for each vehicle programs, there are around 100 to 150 vehicles, they're going to crash the vehicle. So in order to avoid the numerous number of prototypes, they can go for a CAE process in vehicle development stage. So how do we do? We are going to see in the coming slides. So preparing a crash structural model. Basically, it consists of, as I said earlier, pre-processing, solver, and post-processing. So in pre-processing, most of the OEMs use ANSA as a preprocessor or HyperMesh. So it depends on the OEMs. And solver, most of the OEMs are using ls-Dyna, but some OEMs are using different solvers, say like radios or PAMcrash or some others, ANSYS. And the post-processing, you can use any software, but I prefer MetaPost to post-process the results. So what we'll do in pre-processing, basically we discretize the CAD, that is called as meshing. We can go for a middle surface meshing or solid meshing. So it depends on the parts and the thickness. So once the meshed parts are available, then we go for connections between parts, so that if you apply the load to one part, it will transfer the load to another part, and then it will replicate the real-time scenario. So connections enough to replicate the real-time scenario. We need a contact definitions if no connections are available between the parts. So let's see more in detail about the contact definitions in the coming slides. Then of course we need to apply the material properties so that it will behave as like in the real world scenario. Then finally we should apply the boundary conditions, say like gravity load, initial velocity, and rigid wall as like a ground. Mostly these three are used in crash analysis compared to NVH and durability. There are numerous boundary conditions, but for crash analysis, we mainly used rigid wall, initial velocity, and gravity. The next part is once you build a model, full vehicle model with including boundary conditions, output requests, and connections and contacts, you go for a solution. So here we are using Dyna for our solver part. So Dyna will take care of the solving the resulting system of governing equations. So it's a backend. So we don't need to worry about it. We just need to give our input files. So it will solve based on the full vehicle model with respect to boundary conditions and material properties. So once we get the results, we need to do post-processing. So first we should understand the behavior of the model, and we should compare with our earlier test results, so that we could say that my results is 95% matching to the test results, so that we can give our countermeasures and solutions if any issues. So what mainly do in post-processing, we should evaluate the displacements as well as the acceleration of the important parts. Say like for frontal crash, we should plot the nodal displacement in the dash locations and the front end locations. Also, we should compare the deformed geometry with respect to our test results. We should always look the plastic strengths of important parts and stress distributions by using the fridge plot. And finally, we can able to plot the energy curves and the reaction forces from the results. And this is the main process overview. For every OEMs, they have a different vehicle development process. So let me give you some introduction about vehicle development process. So basically, they develop underbody first, and then upper body. In between, they develop a powertrain. But most of the OEMs keep some 10 to 15 powertrains, standard powertrains. They use it for different configurations. They mainly concentrate on the underbody and upper body development. So in underbody development, they have a different stages, say like 1, 2, 3. So the CAD department freezes the CAD for the first stage for the underbody. Then we CA guys will get the CAD from the CAD guys for the first stage to check whether the CAD is meeting the limit, safety limits or not. So we used to get the CAD from the CAD guys. That's a volume CAD. Then we do the meshing of the parts with respect to each assemblies. Once the meshed parts are available, we should apply the material from the BOM. What is BOM? Bill of material. So it has the information of part information, PID information, and material information. So based on this information, we should apply the material to the meshed parts. So now we have missed parts along with material, then we go for a connections realizations. What are the important connections? Important connection is spot welds. So you have thousands of spot welds in our model, but if you have a MWF data, we can easily realize those connections in ANSA. What is MWF data? It's a master weld file data where it has the location of the weld and the part information. Say like for two T welds, say like two tire welds, it has two part information, and three tire welds, it has three part information. So once your connection is done along with the material, then we should assemble the vehicle based on the different assemblies. So once your full vehicle assembled model, you need to apply the boundary conditions, say like rigid wall, initial velocity, and gravity, along with the output request. The output request is based on the load cases. So different load cases having different outputs. Say like for frontal, you need to make output of a dash and the front end and the rump bumper. So it depends on the load case. Once your model is ready, you can directly submit the job to the supercomputing computers. But before that, we should go for a model checking so that you can avoid the basic errors before submit your job. So what should be checked in model checking? Basically, free nodes, free parts, duplicate elements, and material, unassigned material and unassigned properties. So we should check these things so that you will not get any error in the model while running the job. After run submission, you will get the results because every OEMs have supercomputing, so no need to worry about that. They will give you a faster results. So once you get the results, you need to go for a post processing. So yeah, as I said earlier, just give me a moment. As I said earlier, post processing, we need to understand the behavior of the model and to compare the results with the test. So that's why we go for a post processing. Next item is key principles of ls-Dyna. So here we can see some basic things about ls-Dyna, so that you'll have a brief introduction about ls-Dyna. So ls-Dyna is a solve part, but you need to define a deck in ANSA. So basically the structure of the Dyna part is it should start with a star, that is asterisk, always start with star and ends with star end. So every keyword should have star keyword. And then most cards are 8 fields. Yeah. So say for example here 2, 3, 4, 5, 6, 7, 8. So it's called as 8 fields, that is 8 digits. That's one 8-digit field is called as 10 characters. So 1, 2, 3, 4, 5. This is our structure. So your keyword should comply with these rules. For example, your node ID, you can have only up to 8 digits. If you maintain 9 digits in your model, then it's wrong. So preprocessor will not read this node ID. So you just make sure that your node ID should contain 8 digits or less than 8 digits. This part is you can define the comma separated variable too, but for crash analysis it's impossible. It's a huge model. You can use always the preprocessor to output the deck, but for some component based analysis you can do it manually by maintaining comma. So for example, for a node definitions, you can maintain node ID comma the x coordinate, y coordinate, and z coordinates. No need to maintain these fields and the characters. And the default value is always used if the field is blank. So here, for example, here you don't need to specify anything here. If you can leave it blank, so ls-Dyna will take it default value automatically. What are the key concepts? So we should always use preprocessor for crash analysis. It will give you the exact keyword, so you can directly submit the job while output from this hypermeasure answer software. One thing is you can use the primer software. So that is a powerful software for ls-Dyna specific. Once you import your full vehicle model from ANSA, and you can go through the basic checks, full vehicle model check, and it will give you the clear error messages. And once you clear the error message, then you can directly submit the job. So you will 99% you will not get any error apart from the time step error. So what are the units in Dyna? So you don't need to specify the unit system inside the model, but you should your units must be consistent. So in ls-Dyna, we could say that this is A scale, B scale, and C scale. So most of the OEMs use B scale or C scale. So what is B scale and C scale? For example, if your mesh size is millimeter and your mass is kilogram, then you should apply a force of kilonewton. So you should not use Newton units. So if you use Newton units, then it take it as a kilonewton unit, and your results may be. So what we will do, we may not know which scale is used in the model. So for example, if you get the model newly, and if you import the model, what you need to do, you can go to the material parts and check the density. And what I'll do is I'll just check the -6. If it's -6, then I just confirm that they use C scale. If it's -9, I assume that they use B scale. So you can assume that your mass is in ton and your force is Newton if the density of the steel is -9. It's a simple trick, but anyway, you need to check in all the parts and all the parameters. And keyword hierarchy. Yeah, this is the important part. Once you know the structure of the Dyna, and then it's easy to debug the model. So for example, part ID. So what is part ID? Part ID should contain section ID along with the material ID. So what is section? So it has some thickness information and element formulation information, and material, as you know, material properties, it's inside. So there are inside the part, there are thousands of elements defined. So each element should be defined with element ID, part ID, and node IDs. So how the node IDs are defined? Star node with the node ID and the XYZ coordinates. As you know already, each element should have the nodal definitions. So each here, for example, quadrilateral element, 4 nodes form a quadrilateral element. So N1, N2, N3, N4. So each node should be defined here, and each element should be defined like this. And some thousands of elements consist of parts. So parts should be defined with the section cell and material elastic, so that your definition is perfectly correct. In your deck, if you have this information, it's directly, you can, if you import into the answer or hypermesh or primer, it will be read. So if you miss any one of the information, then the information will not be read in the preprocessor. So this is important parts. And then what are the files extensions? There are so many files in ls-Dyna, but I picked some important file names with respect to crash analysis. So mainly for input files, the ends with the star.key or .k. Same like output files, we have .d3hsp, where you can find the mass and time step information. And binode files, you can plot the curves by using these files. And D3 plot, you can find the animations. And GL stat is global statistics, where you can find the energy information and all other global information, internal energy, kinetic energy, and total energy informations. And if your model is crashed out, then you can find the errors in the message files. And if you mostly, you can find the model debug. If you are doing model debug, then you should check out always the message files for error information.